Right, linear congruences I've done. Now I'm going to focus on the Chinese remainder theorem. Which is a wonderful theorem, and again it crops up over and over again in mathematics Olympiads. Over and over and over again. So let's just state it, and then I'll construct a solution. I'll prove it as well. So we've got n1, n2 up to nr are integers which are pairwise co-prime. Pairwise co-prime. Or I think I said relatively prime. You'll recall from one of the earlier screencasts that pairwise co-prime, if a bunch of numbers are pairwise co-prime, that is a more powerful statement than jointly co-prime. So I'm basically saying that if I is not equal to j, then ni nj equals 1. Okay, so there's a bunch of numbers there. So what am I going to do with it? What I'm going to do is say I'm going to solve for x the following. X equals a1 modulo n1, x equals a2 modulo n2, and so on, all the way down to x equals ar modulo nr. And here's my modulos, and they're all relatively prime. They're all pairwise co-prime. Now, the Chinese remainder theorem says that we can solve this, which is nice. Well, it said that's the first thing it says. It also says that the x is unique modulo n1 times n2 times n3 times all the way up to n4 equals the product. Equals the product. Actually, I'm going to write n equals n1 times n2 all the way up to nr. The product from I equals 1 to r of ni. Okay, so this is what the Chinese remainder theorem says. So what I'm going to do is basically construct a solution. Let's just go back to the equations here. So let's just give you an example just to fix ideas. If I just find an example, this is a famous one here. If I say that x equals 2 modulo 3, x equals 3 modulo 5, and x equals 2 modulo 7, find x. And of course you see a whole bunch of equations that are like this. It'll say, oh, we've got a certain number of coconuts, and when we shared them out between three people, there were 2 left over, and then we tried again and shared them out between 5 people, and 3 were left over, and 7 people, and then 2 were left over. How many coconuts were there? You see this kind of question in different sort of silly guises or different silly contexts appearing, but it's all basically the same equation here. So this is just an example, but this is how to solve it. So let's just have a look at this. Let's see how we're going to solve it. Well, basically, n is the product. I'm going to write nk equals n over nk. So it's the product of all the others. So capital NK equals that, and I write a large n to remind myself that it's a big number. I guess I should have written that as a capital as well, but there you go. Now I'm just going to make the observation that nk comma little nk equals 1 because all the n's are pairwise co-prime. Okay, so what I'm going to do is observe that I can solve nk times x equals 1 modulo nk by the theorem or by the corollary to the linear congruence screencast, which was the previous one. So I can always solve this equation here. So nkx equals 1 modulo nk, that always has a solution. And moreover, it has a unique solution because the greatest common divisor of nk and little nk comma little nk equals 1. which is great. Okay, so what am I going to do? I'm going to construct a solution x star, let's say, and that equals. So let's go back to my equations to make sure I've got my notation right. Where are we? Actually, I'll go up here. I'm going to form x star equals, and I'm just going to write it down, a1 n1 x1 plus a2 capital N2 x2 plus dot 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 plus all of them together plus AR NR XR, where XI equals a solution, or the solution I guess, to the equation nkx equals 1 modulo nk. I guess that's k in there. That's xk equals the solution to this equation here. Okay, so I'm forming this sort of massive sum here. So what we're going to do is solve all these guys independently, solve all these equations independently, get all the x's, and then just shove it all in there. Okay, so if I say that if I just make the observation that ni equals 0 modulo nk for I not equal to k, I'm just going to make the observation that capital N subscript I equals 0 modulo nk. Why is that? Well, it's because ni equals n1, n2 all the way up to nr over ni. So the fact ni, wherever it is, has cancelled out from that. And so that means that modulo nk, there's an nk in here as well. So modulo nk, capital Ni is equal to 0 if I is not equal to k. Okay, so if I think about what this answer x star is, I'm going to work out what that is, modulo nk. Well, let's just write it out again. X star equals, sliding about a bit here, a1 n1 x1 plus a2 n2 x2 plus a k nk xk. Well, these are all zeros. They're all zeros except for one of them, which is down in here, which is ak nk xk. And we know by definition that nk xk equals 1 from here, because it's by construction. So x star equals a whole bunch of zeros plus ak nk xk, which equals ak times 1 equals ak. Well, there it is. So we've just constructed our solution. X star satisfies the equations, which are up here, because we constructed it, and then I'm asking what x star is modulo nk. Nk. And modulo nk x star is equal to ak, as it should be from the equations, because that ak there matches this ak in here, wherever it is, mod nk, I guess, in there. So we found our solution, which is quite nice. Okay, so let's think about how to actually solve it for the concrete example which we've got here. I'll write it out again. I'll start again because I'm getting myself a bit quite a lot of stuff here. So we need x equals 2 modulo 3, x equals 3 modulo 5, x equals 2 modulo 7. So what we're going to do is consider 3 times 5 times 7, which equals 105, I guess. So we're going to look at x modulo 105. So n1 equals 3, I'm sorry. n2 equals 5, and n3 equals 7. So n equals 105, which is the product. So n1 equals 35. n2, capital N2, equals 105 over 5, which is 21. Of course, it's the other two. It's 3 times 7, isn't it? And n3 equals 3 5s of 15. So what we need to do is to find the linear congruences. Remember, we're going to solve n I x I equals ai for I equals 1, 2, 3. We need to find that, and then we'll plug it into our massive x star. So we need 35x equals 1 modulo 3. We have got 21x equals, what was it? Oh, that's x equals 2 modulo 3. That is equal to 35x equals 1 modulo 3. Okay, Chinese remainder theorem example. So I'm going to give an example, a very famous example. X equals 2 modulo 3. X equals 3 modulo 5, and x equals 2 modulo 7. So find x. Now the Chinese remainder theorem says that x is unique modulo, oh, these are pairwise prime, of course, because they're all prime, in fact. Modulo 3 times 5 times 7 equals 105. So I guess we could just go through all 105 numbers and find which one satisfies it, but see if we can be a bit cleverer than that. Okay. So how do we do this? Well, we form that we've got n1 equals 3, n2 equals 5, and n3 equals 7. So n1 equals 105 over 3 equals 35, of course. Oh, of course, it's 5 sevens. N2 equals 3 sevens of 21, and n3 equals 3 5s of 15. So you'll remember that what we're going to do is we're going to form our solution x star, which was equal to, in this case, because we've only got three congruences, we're going to have a1 n1 x1 plus a2 n2 x2 plus a3 n3 x3, where the n's are here, the a's are given in the question. There they are, 2, 3, 3 and 2. Those are the a's. And xi is a solution to ni xi equals 1 modulo ni. Okay, so in this case we just have to figure out what they are. So x1, the equation for x1 is 35x1 equals 1 modulo 3, because it's just this equation here for the first one. The second equation is 21x, because that's capital N2, x2 equals 1 modulo 5, this one. And the last one is 15x equals 1, 15x3 I guess, equals 1 modulo 7. There it is. Well, let's find these. x1 equals 1 isn't a solution. x1 equals 1, that's no good. x2 equals 2, yeah, that's good, because it's 70, which is 69 plus 1, so that'll do. Oh, that's x1 equals x2 equals, well, 1 will do because 21 equals 1 modulo 5. What about x3? x3 equals 1 will do because of course 15 equals 1 modulo 7. So we've got our solutions. x1 equals 1. Oh no, it wasn't. x1 was equal to 2. x2 was equal to 1 and x3 was also equal to 1. So going back to our solution here, which is this guy here, we can just whack them in together. See if I put it on the same page. So it's a1 n1 x1 plus a2 n2 x2 plus a3 n3 x3. Oops, let's try that again. So what were my numbers? My numbers were up here, 2, 3, 2. So it's 2 times n1 was 35 times 2 for the x2 there, plus a2 from up here was equal to 3 times capital N2, which was 21 from here, times x2, which was 1, plus a3, which was equal to 2 times capital N3, which was 15, times x3, which was equal to 1. Well, that's our solution. Let's do a little bit more of this work. 35 times 2 is 70, times 2 is 140, plus 3 times 21 is 63, plus 2 times 15 is 30, plus 63. Actually, look, this one here, remember we're considering everything modulo 105. So 140 equals 35 modulo 105, because I can just take away 105 from it. So that's made my life a bit easier. So now I've got 35 plus 63 plus 30. Let's try that. That's 65 plus 63. That's 128. And again I can subtract off 105, which leaves me with 23 modulo 105. So 23 is a solution to our original equation. We better check that. There's quite a lot of steps in this. Let's just have a look at this. What I'm asserting is that x equals 23 is a solution. Well, it's equal to 2 modulo 3. What about this one? Modulo 5, it's 3, as it should be, and modulo 7, well, it's 21 plus 2. Plus 2 here, so it's 2 modulo 7. So we've solved our classical problem. This is from some ancient Chinese text. Okay, I'm going to stop there.